Everyone, April 18th. Alright, let's do this. What's this? Longest zigzag path. You're given a root of a binary tree. A zigzag path for a binary tree is defined as follows. Choose any node in the binary tree, okay? And the direction, right or left. If the current direction is right, move to the right child of the current node. Otherwise, move to the left child. Change the direction from right to left or from left to right. Repeat the second and third steps until you cannot move in the tree. So if the current direction is right, move to the right, and then change to the left. But what if the current is left? Well, how do I know the current is left or right? Root, hold on, zigzag length is defined as the number of nodes visited minus 1. A single node has a length of 0. Return the longest zigzag path contained in that tree. So if I go from this one, that's the root, right? And I go anyway, I don't have a left, so I go right. And then from here, I have two choices, right? I can either go left and then it ends, or I can go right again. But if I go right again, because the previous one is right, so if I go right again, that's not a zigzag. So this has to be, so I need to record the previous direction, right? So in here, previous direction is a right. So I go left, I can keep count. I go right, I have to restart. So this will be restart, right? And then here, if I go this way, I have to restart. I go this way, I can continue. So we're gonna start from the root, right? It's a binary tree. So we start from the root, and then what we're gonna do? We're gonna DFS? Yeah, we can DFS. DFS, right? As we go. At every node, I will know the current length. So I need to also pass the current length, right? Okay, we pass the current length. So every time, if I start, if I don't start, then I pass whatever we have previously and then plus 1. And we just keep moving because every node will visit every single node, right? And every node can be considered as the root, right? Can be considered as root if it can, right? If it cannot be considered as root, then, well, I mean, if you go both directions, and from one direction, it has to be considered as root. So it doesn't really matter. So yeah, I think that should be it, right? We start from something and then just keep going. We go left and go right, and then we just keep counting. Okay, let's try. See if can get it done in one shot. That's not what we need to see. All right. Oh, it's tree, so we don't have test case for this. All right, so we're gonna do self.res, okay? Def DFS. So we need a current node, which can be optional tree node. Actually, it's not gonna be optional because number of nodes, we will never visit an empty node. So we can just go tree node, right? And previous dir. We can do actually str. That's fine. And what else do we need? Previous direction and the current length. Right? Current length, that's an int. And we don't return anything. Okay, so we say when we hit the current one, right? So we start with 0 and then we go on, that would be like 1, right? So we hit. Now I want to be when I hit something, right? When I hit something and then I visit the node and I increment, Okay, I visit a node and I increment, which means when I'm at myself, the previous direction is actually -1. So previous direction plus me, that's the current direction. So I do plus equal 1, right? I visit the current node and I say self.res shall equal to maximum self.res, and that's pre-direction. Come on, man. It's not pre-direction, it's current length. My bad, it's current length. Okay, so we handle that. And then we say if node.left, okay, then we can go left. But that's DFS has to go DFS node.left current length. Oh, it depends. Previous direction shall be left, right? Because this is going left. And the current length depends. We can say pre-direction is equal to right. If previous is right, and then current is left, then we pass current length, right? If else, then it should be -1, right? And then if node.right, then we do exactly the same thing, but we'll do here right. This will be right, and previous is left. And then we just run DFS root previous direction. Oh, previous direction. When you had the root, what's your previous direction? It doesn't matter. It doesn't matter because at root, previous direction does not matter because when I pass in, this makes them passing -1, right? So current length will always be 0. Okay, current length will always be 0. Oh, that's not right. That's not right. Maybe I can do empty, right? So if this is not equal to left, and this is not equal to right, then I can pass in an empty direction, and then it's not equal to, so I can always, so from the start, when we always go, it has to go with the current length. And then we'll return self.res. Okay, let's take this for a ride and see if it works. It does not work. 340, I got 240. That is interesting. 240. Huh. The first one. Okay, we have issue with the first one. Why? Okay, let's do this. DFS root, right? Root comes in, and then current length will be 0, right? And then self, that's just 0. And now we say node.left, it doesn't have left. So node.right, and then pre is not equal to, that's correct. So we pass in 0, right? So we pass 0. So here, length is 0, so +1, length is 1, okay? And then I say node.left, yes. And previous is not left, that's correct. The previous is R. And then I put 1 to it, so this one will give me 3, right? This one giving me 3. We can actually let's print self.res. Just take a look. So that would be 3. And then when this go, oh, maybe I shouldn't do -1. When this go, wait, why is all 2? That doesn't make any sense. Oh, res. I should do current line. Now current. That's very interesting. Current length is 0. yeah, 1 and 2. Yeah, that's right, 0, 1, and 2. And then when you pass to the right, it shall be 0, right? Because that, no, yeah, that should not be -1. When you start is -1, right? But in here, when you're passing down, that is not -1. That should be 0. This shall be 0 as well. Yep. This seems to be right. Yeah, your start can be -1, so we make sure the first one is 0. But when you go like past, this has to pass a 0. You have, because when this one is 0, right? Okay, let's use all the others and then give it a shot. Okay, try it. Okay, yeah, not too bad. Not too bad. So these has to be 0. This and this, they have to be 0. Okay. Sem 1372. Okay, so what do we learn from this? DFS, right? And keep counting the zigzag path. Each time the child's direction is the same as the parent's, reset the count and record the max count at each node. Does that count as greedy? I don't know. No, I think it's just DFS. If node, maximum steps, if go left. Yeah, go left, go right. Yeah, use true and false. That's fine. They do it twice. You see that? They do it twice. For me, I just do it once. I set a -1, and then it takes a little bit. Yeah, that's fine. Okay, so this one's done. Now I want to go back to the problem we had yesterday, and I have this solution. It's actually quite good. I want to analyze this. So this is like DFS and GCD. So to do that, let's brain out OneNote. All right, that was a suggestion from yesterday that OneNote is better. Yes, this is better. I mean, I can tell that this is better. The response is better, right? Everything is better, and what's more, the eraser is also better. Hold on. Right, eraser is also better. Okay, so the ideal is, actually, don't look at this. Let's go to the problem. Okay, so the ideal is the same as yesterday, right? We have bunch of values. Right, we have a bunch of values. And then the goal is to say, given the current value, right, can we find all of, so let's use the, what example do we have from yesterday? This one, right? 5, 6, actually we should move this one here, right? Let me say, we have here 5, 6, 4, 3, 4, 5, 6, 7, and 7. Right? That's what we have. So the goal is, say, if I want to include 5, then in this, right, we want to find all the numbers that can form square free with 5. But the problem with this is we'll have duplicates, right? We'll have duplicates, and we'll have things like 6 and 3. So that's what we had problem yesterday. And these are just not easy to deal with. But duplicates can be resolved by using counter, right? We can just say unique is 7. And then we can have a counter says 7, we have 2 counts. So that's easy to solve. Now what cannot be easy to solve is what do we do with like 6 and 3? So both can form with 5, right? But they cannot group together. Now the ideal is we don't worry about it. We throw this to a recursion. So we say we want to find a 5 with all possible, right? All possible square-free combinations here. And everyone can form with this 5, right? And then what do? We just say 5 is to have 1 count times, we can call it, let's call it, is that dp? It's not dp. It's just, I could call it helper, right? We can have a helper function, and the helper function is just 6, 4, 3. It actually is no 4, 3, and no 5, and the 6 is gonna be counter, so it's unique, so it's 7, right? That's it. And actually this is not 1 because we have 2 5s, right? So because counter it, so this is actually, you know what? It's just it should be 2 times this, right? Now we just need to figure out how many square free is here. And you see we have 6 and we have 3. Then we know if we can figure this out, we can eliminate all the false positives, right? So with that, it becomes actually quite straightforward. So what we need to do, right? What we need to do is to get a counter, okay? And after we get a counter, now there's also another piece, is from 1 to 30, right? The number of integers that itself does not contain square is limited. We have 2, 3, actually right, no 4, 5, 6, 7, no 8, 9, 10, 11, 12, 13, 14, 15, 16, no, 17, 18, no, 19, right, 20, no, 21, 22, 23, 24, no, 25, 26, 27, no, 28, no, 29. That's it. That's all the values that's, possible, right? Possible. So we can just take this as the base, right? We can take this as the base, and then we say, if I want current is 2, right? How many we can form, and then we can see if we have any 2s in the original, right? In the original. If not, it's just going to be 0, which is fine. And now we can say how many 3s, how many 5, how many 6. Just do this. I mean, it's because this list is small, so it will definitely work. So that's kind of the basis of that method. So I want to try it. I think it's good. Something different, right? Something different. And we don't have to factor, that's the thing, right? We don't have to factor because we can say the base, right? We can call them the base. So base is 2, 3, 5, 6, 7, 10, 11, 13, 14, 15, 17, 19, 21, 22, 23, 26, 29, right? That's it. That's all we have. 2, 3, 5, 6, 7, 9, 10, 11, no 12, 13, 14, 15, no 16, 17, no 18, 19, no 20, 21, 22, 23, no 24, no 25, 26, 27, no 28, no 29. Yeah, that's all. Oh, 30. Forgot 30. Yeah, forgot 30. So we have 30 as well. Then what? Then we have the base, and we need a counter. Okay, counter, we say counter nums. Do we have a counter? We don't have a counter, so we have a counter. All right, counter nums. This is to get unique, right? Get unique counts of elements in nums. Okay, and then we can do def helper, and helper we just need to pass in a list. So we can say a list is a list of integers, and this one will return an integer. So this we say find, right, the number of square free subsets in list. Okay, we say if not list, return 1. If we don't have anything, then the square free subset is 1, which is empty, right? This is empty set. Otherwise, right? Otherwise, then we will always take, we say we want the first element of this list, try to match with the remaining. Okay, and then we want to know which ones can form a square free with the first one, and then the method is use GCD, right? So let's say we have 6. 6 cannot form with 2 because GCD 2 and 6 is not 1, but 5 can. So what we need to do is say next list, right? Next list shall equal to for L, for element in list if math.gcd, right, element and list 0 is equal to 1. If that's true, we will record the element, right? That's the next list. Then what we can say is the current count, right? So the count of all lists is return. We need to mod as well. Hold on. Let's get the mod. Right. So will be either we do not use list 0, then that will be helper list 1, right? If we do not, I mean, yeah, that will be copying the lists. So maybe, you know what? It's okay. It's okay. So this is not using any list 0, or we use list 0. Then we say counter list 0. So we don't know how many counts is in the actual numbers, right? So we do counter this multiplied, right? Multiplied by what? Multiplied by helper next list, because this can only form with all the combinations of the next list. And of course, the whole thing we need to mod. Okay, that's the helper function. Okay, now we can actually just say helper base, right? Helper base will find all of them. But then we have to handle a very ugly case, is nums equal to 1. So what if we have nums equal to 1? Well, when we have num equal to 1, we can actually think about it. If num equal to 1, what does that mean? Right? Num into 1. Let's say we have a 1. Right? Let's say here we have a 1. Right? That just means anything we have, we find here, can also form with 1. Right? And if we have multiple ones, right? If we have multiple ones, right? Then this should be the combination of everything here with doing this. Therefore, we have to do the helper this, right? Plus, right, plus, I feel like it should be the helper base time. So that's actually this times 1 plus counter 1. Right? I want to know counter 1. How many of them? And that should be 2 to the power of this minus 1. which we can cancel these two. So I should be like this. And this will mod. Now we return this. Okay. Wait, solution 1. This is solution 2. Does it work? Does not work. Something is not right. Anyway, let's take a look. Inspired by this solution. Why does it not work, man? What did I do wrong? Okay, don't look at it first. Interesting. I'd like to take a look. Result 4, answers 3. I got one more. Wait, hold on. Did I get one more for all of them? Yep, I got one more for all of them. Why? Well, because that's interesting. I have one more than all of them. I know why, because the solution actually tells me, but I like to figure it out. Let's take a look at this. Okay. If you do 1 and 1, and you pass it in, then everybody will be empty, right? This will be empty because list 0 start with 2. So that will just be empty. That's a 0. And 2 to the this, 0. Well, I mean, you go to the end. This is empty set, right? The last, this is empty set. So empty set plus, so it'll be return 1. And 2 times, 2 to the counter, that's actually 2. Huh. Did you forget -1? Oh, I did -1. 2 to the power, right? -1. But we also have the +1. Yeah, we have the base. Helper base, right? So we say how many we can form given this, right? And then so including this, all the way. At the end, we'll have empty, right? This will be empty plus whatever I have times, so what I have will be this thing times this will be empty, so it'll be 1. So empty, because at the end we have an empty, therefore we have the -1. Note that helper will will work on an empty set, right? So its result must be deducted. There we go. Oh, hold on. I need to like that solution. Yeah, I still think bitmask is more intuitive. This is actually a harder one, but damn, it's fast. Very fast. it's basically, you can call this a 1 because the base is only that big. Okay, so that's that. Yeah, I like this solution. All right, what's the next one? Yeah, we can work on this a little bit. Find the string with LCP, longest common prefix. Oh, I do not like string. Define LCP matrix of any zero indexed string word of n lowercase English letters as a n by n grid such that LCPIJ is equal to the length of the longest common prefix between the strings word I to the end and j to the end. Okay? Given an n by n matrix, return the alphabetically smallest string word that correspond to LCP. If there's no such string, return empty. Okay. All right, let's give this a shot. See, this is the good part. I can just create a new page. All right, so LCP, right? LCP. So we have we have 4. 1, 2, 3. 1, 2, 3. What do we have? 4, 0, 2, 0. You know what? Maybe I should make it smaller. Maybe I should make this thing smaller. Yeah, I don't need this one to be too big, at least for this current phase. So we have 4, 0, 2, 0, 0, 3, 0, 1, 2, 0, 2, 0, and 0, 1, 0, 1. And the corresponding to position 0, 1, 2, 3. So this is saying from start to the end, the prefix, oh yeah, there's always going to be 4. Always going to be the length. So this is useless. So basically we want to know, this is a string, right? 1, 2, 3. So what are everything here? And the diagonal is useless, right? Diagonal is useless because it's always going to be 4, 3, 2, 1. And the bottom half is also going to be useless because they'll always be symmetrical. It's a symmetric matrix, so we don't need to worry about the bottom. So no bottom, no. Why don't you just erase them? Look what you did. It looks awful. It's actually not that awful. We just. Okay, so now we focus on here, right? So we say from 0 to the end, okay, from 0 to the end, and from 1 to the end, right? There is no prefix, right? No prefix. So we basically say 2, 3, 4. How can I represent it better? Position 0, 1, 2, 3, and then 1, 2, 3. We have no prefix, which means these are not equal to, these are not equal to, and these are not equal to. Right? And actually 0, this is always going to be A. Right? This is always going to be A. And because 0, 1 is 0, which means 0 is not equal to 1, so 1, the smallest, is going to be B. Right? And then 1 is not equal to 2. It cannot do C because it can be A. But let's stop right here. Okay, so I say 0 and 2, right? So I say 0, 1, 2, 3. 0, 2 is from 2, 3. That is 2, which means 0 equal to 2 and 1 equal to 3. So 0 equal to 2, which means this has to be A. And a 1 equal to 3, so it means this has to be B. So it's A, B, A, B. And we check 0, 1, 2, 3, and a 3. 0 and a 3 is not equal to. 0 and 3 is not equal to. Yeah. And then what? Do you check again? 1, 2. I mean, using one line, we already got it, right? For the first one, using one line, we already got it. Let's keep doing it. Okay, so this is 1 and 2. So we have 0, 1, 2, 3, right? So 1 and 2, so 2, 3. So what we get is 1 is not equal to 2 and 2 is not equal to 3. So 1, I say, is B. And 2, these are not the same. Well, they're not the same. They have many different ways for them to not be the same. It could be A, it could be C, it could be anything, right? And 2 is not equal to 3. Yeah, that doesn't really work very well. I think the most information rich is the first row, right? The first row always is the most information rich because the first one is always going to be A, right? The first one is always going to be A. So we know the first one. So we want to know who the first one is equal to, right? Or the first one is not equal to. So it's this position, right? This position will give us a lot of information. This position will give us a lot of information because that's 0, 1, 2, 3 to match 1, 2, 3. So we will have 0 and 1, right? That's the only time 0 is compared to 1, and they are not the same. So if they're not the same in this position, I can do C, I can do many things, but the best is always going to be B, right? So we check this, right? If this is 0, right, then this will be B. If this is 1, then this will be A. And then we need to check this position because that's 1 compared to 2, right? And honestly, no, because when this one we know is B, right? When we know this one is B, the next one is hard to, unless these two are the same, right? Unless these two are the same. So what do you say? I say we do the first row, right? And you know what? Let's try another one. Let's try another one. What's the next? 1, 2, 3. 1, 2, 3. So next one is 4, 3, 2, 1. 3, 2, 1, 2, 1, and 1. Okay. So we say 0, 1, 2, 3, and then 1, 2, 3. I have 3, so which means 0, 1, 2, these are all equal, right? So we know we start with A, right? We know the string always start with A. So the first is equal to, so this has to be A. So this has to be A. This has to be A. Done, right? So by looking at this one alone, we already know. So yeah, so by this we will know some information, right? If it's 1 smaller than this, right, that means everybody will be the same because it's the remaining to compare with everything else. And if this is, let's say if this is 2, right, if this is 2, which means these two must be the same, so it has to be AA. Now it has to be AA here, right? If it's 0, that means this one is B. If this is 1, that means this one's A. If this is 2, that means we have 2 A's. If this is, like, however many this is, we'll fill how many A's here. And once we're done, we can look for the next one. Right? The next one will be 0, 1, 2, 3 to match with 2, 3, right? So that's what we match. Then, since we already filled, right? This one we filled, this one will fill no matter what value this is. So this one will fill. So by doing this, we can fill these two values. If they're the same, then we can fill this. If they're not the same, if 0 and 2, if these two are not the same, then we'll always return back to A. I'll always do B, right? If these two are not the same, I mean, if like this is 0, right? If it's 0, then this position will have to be B, right? And this we will not know, right? This we will not know. So if it's 0, we can only fill one value. If it's 1, we fill 1. If it's 2, we fill, well, we'll fill this. Okay, I want to try the last example. Last example. It's a good test case, last example. So last example is that's basically the failed case, right? So we have 4, 3, 2, 1. 3, 2, 1. 2, 1. And 3. Well, so how do we check if it's not possible? Right? Like we can probably get it from the first one. Oh, we need to check if the second one works, or the third one works, or the last one works. I mean, we can check the diagonal, right? They each has to be decreasing, right? Each has to be decreasing. That's actually not true. 4, 0, 2, 0. That's not true. So it's just the diagonal has to be decreasing, right? Or we can say that every diagonal has to be decreasing. Yeah, because this is 0 position, 1 position, 2 position, 3 position, right? So this will have 4. This is just n minus 1, n minus 2, n minus 3. So this mostly is 1, right? So we still have to check every single position just to make sure that it's correct. How can we check it fast? Is there a way to check it faster? It's 1000 by 1000. So the first one, we can probably get some, right? And then the second one, yeah, I think the easiest might just be just go through them one by one, right? And then to check how many is the same. But it will take a long time. It will take a long time. Huh. And whatever is fitting the first one. Yeah, the first line is already deterministic, I think. Just by the first one, you're already deterministic. Because the first line, the first row, already tells you, right? Already tells you what's what. It tells you how many are matching, right? And then it will keep telling you how many are matching. So from the first row, we shall already obtain the string. Now the question is, how do we produce the remaining, right? How do we produce the remaining such that we can check if they're correct? So basically, yeah, the first line, this one's good enough, right? No matter what this line is, it's already good. And no matter what it is, because you have 0, 1, 2, 3 compared to 1, 2, 3, you have 0, 1, 2, 3 compared to 2, 3, and 0, 1, 2, 3 compared to 3, right? And then this is always no. So when this is no, this will be known, right? One position you'll know. And then if it's the same, right? If it's the same, if it's not the same, the first time we hit not the same, we will set it and then we'll break, because the next one we're not sure, right? Next one we're not sure. So if it's the same, then this is no. If this is the same, this will no. If this is not the same, then this is actually no as well, but we'll break there. And then we go to the next one, and then at least we have 2 no for the first one. So this can tell us, right, if this is correct, right? And then, yeah, this will tell us if this is correct, and this is correct. And that will take boom, 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 boom. Yeah, we're actually just comparing them one by one. Anyway, the first one we get how it is, and then how do we check? I mean, this we can check. Diagonal we can check. Diagonal is easy to check. All right, diagonal is easy to check. And how about this diagonal? Can you check really fast on this diagonal? Like after we get the first one. So for this diagonal, what we are asking for, like for example, this thing is 1, 2, 3 compared to 2, 3, right? 1, 2, 3 compared to 2, 3. Then how do we check this fast? Well, if you think about it, we already did this comparison, right? In this position, we do 0, 1, 2, 3. Check with 1, 2, 3, right? So we already know we have the total of this. We already know. Oh, but if this is not the same, then this will give you 0. But these can still be the same. Like these can still be the same. So what do we say? We say diagonal wise, we have this value, okay? And then we go this. So for one thing, diagonal wise, this will never be larger than this. Agreed, right? They will never be. If this is 3 and this is at most is 2, so at most it has to be -1, right? If it's -1 or it's smaller, that means it works. But if this is 3 and this becomes 1, right? Then it doesn't work, which means all of these are equal because it's 3, or they're equal. Now we come to here. Now we say this is only 1, and that's wrong because this is equal and this is equal. I already know because of 3, which means whatever this value is, right? Whatever this value is, because that's the prefix, right? That's the prefix. So when we go to the next one, if this is 1, which means we just have the first one equal, and then the remaining, at least this one does not equal, then the next one must be 0, right? If we only have 0 and 1 match, and 1 and 2 does not match, doesn't care if 2, 3 match. We just care if these two match. These two does not match. So we go here. It has to be 0 because you're trying to find this and this. Okay. So if the previous one is 2, say I have to say these 2 matches, and this one does not match. 2 and 3 does not match. So when we go to the next one, it has to be 1. It has to be 1. Yeah. And if all 3 matches, And the next one, like if it's 3, then the next one must be 2. So diagonal wise, if we have a value, a non-zero value, the next one must be -1. However, if, so let's do this again, 1, 2, 3. If none of these match, which means diagonal wise we have a 0, then the next one is we don't know, because this actually these we don't know. It's not equal to. We don't know. What we only know is this is not equal. So if we move on to the next one, and we need to compare the prefix of this, basically, we do not know. So if we do not know, we have to do it, right? We have to actually do it. We have to check. Therefore, whenever we have a non-zero diagonal, then this we can directly check by this -1. If it's a 0, as in the case of this case, right? This case we have a 0, right? We have a 0. And it's actually just, we can only say the second one is B, right? This one we don't know, this one we don't know. And then because of this is 2, then we know this is A and this is B, okay? And the last one, we have to check as well. Okay, now that we checked everything, right? Now that we checked everything, now diagonal wise, this 3 we have to check. See if it's smaller than, see if it is 3. You know what? We might as well just check the diagonal first. That'll be easier. No, I don't like that. We make sure the first is good, and everything we can say, okay, this is 4, so it's just a 3. Now this one, because previous is 0, so this one we have to actually check, which is we have to do BAB to check with AB, right? We have to check. Basically, just if the first one is not equal to, then 0, it's good. And this is a 2, so we only need to check if it's 1. It's 1, it's good. Now this is a 2, so we check. This is 0, so we have to redo. So it's going to be AB to check with B, and that's a 0. That's good. And the last one we check with this. So maybe that's the way to go. Maybe that's the way to go. So I am going to try. Let's give this a shot. Okay, let's give this a shot. I don't need this to be that big. It's fine. This is good. Okay. Right. And this one I can get a little bit bigger. Okay, I'll give this a shot. Okay, so we're gonna say the string, right? Res is gonna be len LCP, right? So just this times n, doesn't matter. And then we will check the first row, right? First row, and we say if LCP 0 is not equal to n, return empty string. Okay, that's the first check. And now we want to do the first one, right? And how are we going to do it? We're going to say we are at, if you take a look, we are at this position, all right? So J is, so we have 0, 0, 1, we get a value, okay? And then the rest, actually res 0 is going to be equal to A no matter what. And then we can just, for J in range 1 to n, okay, J in range 1 to n, and we can say, we can give a value, right? We'll give a value. And then we say for P and Q, right? For P and Q. And say for P in range J to the end, for Q in range J plus 1 to the end. That's actually not to the end, n minus 1, because they need to match, right? So everything is going to be, that's actually not true. It's not, maybe I should do, so P is going to be J, right? Yeah, J position. No, actually, no. It's a 0 to the end. Hold on. So P shall go from 0 to the end, right? And then hold on. So J, we're doing this, right? So we're gonna have 0 to the end and then this to the end. So I shall say for P in J to the end, okay? For P in J, for Q in this, P shall equal to Q minus J. Does that make sense? Right? P shall equal to Q minus J. So if Q is at 1, then P is going to be 0, right? And then Q, whatever it is, we minus it from the start. Okay. Then what? Then we need to know the current count, right? The current count. So all the counts shall be the same. So that's not 2n. That shall 2j plus LCP 0j. That's the total count, right? If we have 1, and that's just by itself, right? And then we know the rest Q shall equal to res Q minus J, right? Q minus J. And we need to know whether it's reaching the end. And how do we know whether it's reaching the end? So Q is J plus, so if in this case, right, it's a 0. What if it's a 0? It's a 0, then Q is not moving. You know what? I'd like to do this way. While Q is smaller than J plus LCP 0J, then we'll do this, Q plus equal 1, right? If when we get out, the Q is, if Q is smaller than n, right? If we have filled everything, then when we at the end, we shall go out, right? We shall go out. If Q is smaller than n, then we can say if Q is smaller than n, which means we haven't gone to the end, right? We are ending at Q. So that's the position where they do not equal, right? They do not equal. Then that position, res Q, must be a B. Okay? Then we go to the next round. Right? Now we go to the next round. We go to the next round. And then we'll do the same thing. Right? If we say these are equal, then we'll just keep filling them. It's okay. We just keep filling them, right? That's fine. Then we need to check if it's correct. Yeah, we need to check if it's correct. Oh, how do we check if it's correct? We check. If it's not, hold on. So what we know is everything inside is the same, right? We shall do if res q is equal to this, then we hold this. Else if res q is not equal to res q minus j, right? If that's the case, then we'll return -1. Right? Okay, want to get out? Same thing. If res q is equal to this, then I'll set it to b. Because you're not the same, everybody else is the same. Actually, really, we set it to b? Or we just don't care about it? Well, we first start, right? And then if there's something that's not the same, hold on. The first start, we have a, b, and then add. This one is we already handled. So the first we'll get a 2, right? And then the next one will fill. Yeah, we'll fill, at least we'll fill the first one. The first round will fill 2 values. We'll get this value, maybe even more, right? And then the next round, right? So it's 2, 3, right? So fit 2, so it'll be 2, 3. Even if we have more, and we have more, we have 2, 3. So these two we can always check, right? We always check. If they're equal, then we fit. What if they're not equal to? What if this 0 and this is not equal to? If it's not equal to, oh, if it's not equal to, oh, it's actually complicated. Hold on. If this is not equal to, I will have a and b, and this position is not equal to 0. Can we call this b? No, we cannot. We cannot call this b because we do not know whether these two are the same, right? 1 and 2, if 1 and 2 is the same. If 1 and 2 is not the same, if 1 and 2 is not the same, and these two are also not the same, then that shall be an A. No, that shall be a C. I think I have to rethink this. Hold on. So I know starting is A, right? Then we check 0, 1. We check 0, 1. Right? We check 0, 1. If 0, 1 is a 0, that's going to be B. If 0, 1 is a larger than 0, then it's going to be an A. Right? Then we'll check this. This we need 0, 2 and 1, 2. If 0, 2 is 0, that means these two are not the same. If 1, 2 is a 0, that means these two are not the same. And depending on whether these two are the same, then we can get this value. Right? So what we can do is, if this is equal to 0, which means they're not the same, then the candidate of this is starting with B plus. 1 and 2 start with B plus. And then we find the maximum of these two. That shall be what value this one is. So you're saying at every position, you will count, right? Like if I want to find this, it's going to be this, this, and this. Maybe that's the solution. All right, I'm going to give this one more drive. All right, maybe we should just do the diagonal. Yeah, let's just do a diagonal. Let's say for I in range n, if this I, right, is not equal to n minus I. Does that make sense? We start with 0. So the first one shall be 4, right? 1. And then all the way to the bottom, last one is n minus 1, so last one should be, yeah. So if that's the starting point. And then we shall say for j in range 1 to the end, right? And for each j, we need to go I. For I in range 0 to, it's actually 0 to, shall we say this position, right? This position we do 0 to 1, so it's just 0. Do we need a 1, 1? Yeah, we can actually check 1, 1. 1, 1 shall be, oh, we actually don't know. That's okay. So we just go to the 0 then. Because in that way we check 0, 1, we'll check 0, 2, 0, 3, and then 0, 1, 0, 2, 0, 3, 1, 2, 1, 3. Yeah, I think we do check every single thing. So that's from to j, right? We don't include j. Okay, so we say if candidate, right, cand is 0. That's a very interesting idea. I think that's what, 64 or 97? I think it's 97. I think it's 97. 97, ord A. Yeah, that's 97. So we start with 97. Oh, with this I can just do 0 then, right? Then candidate is 0. That's fine, doesn't matter. So we say if LCP from I to j is larger than 0, right? If it's larger than 0, then candidate, what type of situation will cause a trouble? A trouble will be, actually there's no trouble because the way we're doing it, right? We just checking, like if it's a 0, that means we have the minimum possible, right? And I have a minimum possible. We try it. If it's larger than 0, right? Then we have candidate equals maximum candidate and res I, right? Because from I to j, right? From I to the end and j to the end, we say the prefix length is larger than 0. So the I and j must be equal, right? I and j must be equal. Okay, and then, oh, if it's larger than 0, then that shall be it, right? Then that shall be it. Then if it's that, then that shall be it. Right? I mean, if it's equal, then we have what this j position is. We know what this j position is. We know the j position. So whenever we have a larger than 0, then we know this j position. And I is keep going on, right? So I keeps going on, and then we can check if it's correct. Hold on. Wait, it's easier. Let's do this one first. Easier is this. J if it's equal to 0, right? Which means we don't have anything. Then candidate will equal to maximum candidate and the res I plus 1, right? That's what the candidate can be. And then else, which means it's larger than 0. Well, if it's larger than 0, now we have an issue, is whether the candidate fits, right? Whether the candidate fits. And how do we know if the candidate fits? Then we shall say, because we have to match with res I, right? We have to match with res I. Then we say, if res I is larger or equal to candidate, then candidate equal to res I, right? Yeah, if it's not equal, it's fine. We don't have a. Ooh, we do have to check this one as well. Hold on. So if they are equal to 0, which means this and this must not be equal, then I have a candidate, right? I have the current possible, smallest current possible there. And if these two are the same, then we have the plus equal 1. If these two are not the same, then candidate can remain as is, right? If these two, yeah, it doesn't have to be res plus equal 1, and just be candidate shall always start with 97, because that's A, right? That's always the smallest. So if it's equal to 0, which means these two are not the same, okay? Not the same. Then we say if these two are the same, then we should say if candidate is equal to res I, then candidate has to at least 1 larger, right? If they're not the same, then it's fine. Then we don't have to do anything. Okay, this is when they're the same. If they're not the same. If they are the same, right? So we have more than 1 prefix, then the result That's what we done previously. We say if it's larger than the candidate. Or maybe we should say if it's not equal to candidate. If it's not equal. So candidate is the smallest we can find so far. So if the result is larger or equal to candidate, then candidate will do this. I think this is correct. Else we're saying the result is smaller than candidate. So it's a smaller letter. And it has to equal. And the candidate is already larger. So I think that is going to be a -1. Well, it's going to be an empty case. And then blah, 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 blah. If everything fits, right? If everything fits, then we have a candidate. Then we just say res j, right, equal to candidate. Right? And then we'll keep going, and then we'll return this dot join for C in candidate. We do chr C. Oh, and there's also another thing, right? If candidate is larger than, what's Z? 122, right? If larger than 122, Z, then we'll return -1. Otherwise we do this. Oh, I am not sure. I'm gonna try it, but if it doesn't work, then we will consider it some other time. AB. This is A. This is impossible case. And also, here's another thing. If candidate is larger than this, right? And we say if candidate is smaller than, well, if res j, if we already filled res j, well, why would you fill res j? No, you will not fill res j, because you go j is 1 by 1, right? So yeah, that should be fine. So we have LCP, and this is find the string LCP. Does this work? Oh, it's not canned. Res Lord R. These work, but yeah, I'm not confident at all. This one. Well, we got something wrong at the beginning. All right. We want to, okay, let's just do this one. Let's just see what we got wrong. Yeah, I'd expect to be a lot of trial and error in this one. Okay, let's see. Let's go back to here. Let's get a new one. So what do we have? We have 2011. Okay, 2011. 11. Diagonal. It's not diagonal. So what I get AB. AB is correct, right? Yes, AB is correct, but the problem is with this. So we have to check diagonal first. Okay. That's fine. We can check diagonal. So, not diagonal, check if it's symmetric. Oh my god, is there an easy way to check if it's symmetric? Anyway, so we say check diagonal, right? And then we say check symmetric. Oh, how do you check symmetric? For I and for j. So for I in range n, okay, for j in range, we do I plus 1 to n, okay? Then we say if LCP ij, right, ij is not equal to LCP ji, that's symmetric, right? For each row, right, we'll get this. For I is 1, so we go 1, 1 will be 2, right? This is 0, 0. So it's 0, 1. So if it's 0, 1, we need to check with 1, 0. Yeah. Okay, so if this is the case, then we'll return this. Check symmetric. Okay. Okay. Yeah, let's see. How many trial and error do we need? All right, if this one fails, then I'm gonna call it a day. And we'll go back, think again. Ugh. Oh yeah, this cannot be 2, 2. It has to be smaller. I can do this. I can do this. It has to be if this or LCPij, right, has to, if it's large or equal to the remaining is going to be n minus j, right? So if j is 1, the maximum is 3, so it's larger than this. And in this case, is 1, j is 1, n is 2. 2 minus 1, the maximum is 1, but this is 2. So this shall hold. What else? Feels like there's just a lot of these cases I didn't think about. All right, third shot. No, we have to check the other one as well. Grr. I have check the other one. Ji is larger than n minus I. Let's see if that's the reason. Not 100% sure, but all right, that's not the reason. But anyway, all right, well, we'll think about this tomorrow. We'll think about this tomorrow. All right, I'll see you guys tomorrow. Adios. Wait, hold on. All right, I think the first, let's go back to this. Zigzag. Okay, so the zigzag, right? Let's see if I can draw it here. All right, let's say we have zigzag. I just zigzag. I think that's the first. What else? Oh, I already got it wrong. Now I have one here, and one here, and we have 2 more here. All right, so we start from this node, right? We start from this node, and the way I think about it, when you do DFS, right? When you do DFS a node, right? And whatever else you have, then I want to visit this node. So when I call this function, right? When I call this DFS function, this node has not been visited before. So now I'm visiting this node. And for this function, we need to know the current length, right? So I have the length, so I have the current length here, and I also have the direction, all right? So I have these two in it. So I'm visiting this node, therefore the length has not included the node. That's why I have to first increment the length. So that's why I have the incremented first. And then usually we'll consider the edge case, right? When the recursion ends. Well, the recursion will end when we don't have anywhere to go, right? And in this case, I am setting up my recursion in such a way that I will never hit a case where there's nowhere to go. So where nowhere to go is like the node is a none, right? This is an empty node. But we see, if we say here, the number of node is 1, right? Therefore, will never be past a empty node. Therefore, we don't have to check the node. And on the other hand, if at each node, we will check whether we can go to the next one, right? Then we can avoid the case of hitting an empty node. So that's why I don't have any check for empty node, right? That's it. Basically, you can think of this as there's no explicit check on the edge case. Why? Because I will never reach an edge case. So anyway, so this is the first line, which is I'm visiting this node, so I have to increment the length. Okay, now what's next? Next is once I increment the length, I want to know if the current length is the largest. So therefore we have the second line, right? The second line I set this is the second line because this is the result. I'm going to check. So I always check if the current length is the maximum length, right? That's the second line. And moving on, the third one, now we're gonna DFS, right? So we finished the current node. Now we need to go either left or right. It's a binary tree. We only have 2 directions to go. And like I said, I will not end up with a case of going into an empty node. Therefore, I will check first. I say if node dot left, right? Just basically check. I mean, we cannot do this. It's fine. We can just call node dot left. Then if we just call node dot left and go there, then we have to put a check at the front. But because I checked it first, so there's no, so we will not end up with an empty node. What the hell? Okay, so we check node dot left. Now we just visit. So this is just visit, right? We have to visit node dot left. But now we also need the direction, right? We also need the current length. Now the current length is just, actually current length is a little bit difficult, a little bit complicated. So we leave this, the direction is easy. The direction is just the direction that I'm go to the next one. So if it's left, I say the direction is L, right? Now the length. So the length, so what is the length? Now the length, it depends, right? If the previous direction is going to the right, which means the parent, right? The node is the parent. If the parent node is arrived by a right direction, and now I am going left, so that's a legitimate move, right? That's a legitimate zigzag move. Because of that, I say I can keep this current length, right? As long as if the previous direction is not left. If the previous direction is not left, then I can always be a legitimate move. But else, if the previous direction is a left, then we are having a left-left situation. Now the left-left situation is bad. It's not a zigzag. So we need to restart, right? Restart. Now here, restart, we have to be 0 because 0 is the current length of a node if you start from it. Right? You think about it. We have a node, we visit the node, and after we visit the node, the length currently, if we restart, is going to be 0. That's why I'm passing 0. This is also here while it's 0. Yeah, so that's just go to the left. And of course, after we go to the left, we have to go to the right. Right? We can say again, if node dot right, right? We do the same. We say DFS node dot right, and because we're going right, so the direction is right, and then current length again if the previous direction is not right, and else it's going to be 0. Yeah, so that's that. So that's the DFS, right? Very straightforward. Now the benefit of doing it this way, because I checked, I saw the solution, the official solution. The benefit of this is when you call DFS, man, this pen is also giving me this trouble. I need to not use the switch. Anyway, so the benefit is when you call DFS at a root, right? You will go root. And then this is the direction. So what direction do you put, right? And what current length do you put? So that is determined based on how the function is defined. And then we see the function is defined by, we visit the node, we'll increment the current length. And then we know if we go to the root, and after we visit the root, the current length must be 0. So that's why this is put in -1, right? Because we go to the root, and then we have the +1. So it has to be -1. And here, the direction. Now the direction is also we concerning based on how we implement here. So we say here, we say direction is not equal to left or direction not equal to right. So it's like a not equal to, right? So basically, if we go to the root and we want from the root to go left or right, always legitimate, right? Therefore, we cannot set this to left. If we set this to left, then the next node, if we go left, that will be illegitimate, right? That's wrong. Nor can we set it to right, because I set it to right. If the next one goes to the right, that will be illegitimate. So the only way to set here is something neither left nor right. And in my case, I just set it to empty. It doesn't matter. You can do whatever. You can do a star. You can do a plus sign. You can do anything. As long as it's not L or R, then it will work, right? So that's just the start of the DFS. And at the end, we save everything in the res. So we just need to return self.res. And that is basically how the zigzag is done. Okay. So yeah, that will be it. And yeah, this one takes some time. This one will take a while. I need to think about it. Probably play with these test cases again to see where I got it wrong. Yeah, I think the difficulty is never. Oh, you're welcome. The difficulty in this is never forming the string. I think the string is easy to form. And in fact, this is wrong. This is 4111. How did you get to? Yeah, that's not right. This is not right. How come my check didn't work? Anyway. Yeah, that's okay. Don't worry about it. But anyway, this one we'll deal with this tomorrow. And tomorrow I'll be traveling, so yeah, it will be a little bit difficult to do this. But we'll see. Maybe if the internet is now good, I have to record it and then upload some other time. Anyway, I'll hopefully see you guys tomorrow. Adios.